lab in Chicago and came in Japan. And he was awarded with Xerox Excellence in Science and Technology Award for distinguished work in creating new business value, productivity, and effective transfer of research technology to new generation of products. So let's join me welcome Dr. Methsa.
Actually, this is late in the evening, so I would like to make this very interactive. So you can ask me questions right in the middle, and then go from there. Because I actually prepared the talk for about 30 minutes, and I realized that I could do it 1 hour. So the best thing is to kind of have communication, direct communication with you, and have conversation. Another thing is I'm coming from a company, not from academia, so where we also do a lot of academic research. Just that our legal does not allow us to put more details. So slides do not have a lot of details, but I can give you some details if you ask me questions. Otherwise, so whatever is in the slide is going to be delivered here. Okay. Other thing, we in Xerox are very keen on patent. I remember patent comments. So everybody is very mental inside our research. We have about 5 research centers now. Actually, yeah, we had 4 now. We added 1 more. So Colorado Research Center, I think about 2 years ago, where we did a lot of computing revolution. We have Xerox Research Center in Webster. That's where I come from. Where we did a lot of work with printing, on production printing. And I gave a couple of talks here before. So I'm not sure what's the real that. And today's talk is not going to be we also have a research center in Canada where we do materials research. We need to looking for a job in materials space part of Canada. They do have some openings. And we have a research center in Nova, where we do some of the linguistic work and computer science research and we have 1 more, that is the recent one in India. It's moved to Bangalore very soon, where we do a lot of the internet-related research, outsourcing research. So if anybody is interested for a position in research centers, we do have some open, and you should try.
Yeah. Does it work?
Yeah.
Okay. By the way, I have to thank the National Science Foundation because we received a couple of grants and we have one active with the University of Illinois. That has been tremendous boost for us because internally, the people who are engaged with academics, they find it very valuable. Even though the money doesn't come directly inside the corporation, but it allows us to work in collaboration. So please do encourage that kind of research. Okay, so that's enough for some advertisements. What I'm going to talk to you today is related to non-printing applications. Why non-printing? Because Xerox is known for copying and printing, color, right, so laser printing and things like that. So why are we going into non-printing area? It turns out that printing, I don't want to say printing is dying. Printing is slowly decaying. So it's people are getting used to this, mobile devices and trying to reduce cost, either office space or at home, smart homes, where they do not want to keep hard copies. They have hard copies in these CDs, right? And they want to minimize use of toner, use of ink. Okay, so I think you may have seen it in your houses. I print less today, even though I use HP printers at home. I don't print that much because the ink costs too much. Okay, so that's why we are trying to change our business slowly. Okay, so we are still doing printing, and we are looking into non-printing spaces. So we acquired a company called ACS, which is affiliated computer services company. We acquired it last year, and we got about 16 new business units into the company. And that is where we are starting new research projects. One of them is transportation. Like, for example, Easy Pass. Every one of you must have really gone through the Easy Pass once or twice, right? So that Easy Pass is actually managed with Xerox. It is the Xerox system now. Okay? we have photo enforcement. Well, we don't want people to drive too fast and get killed. Yeah, or that could be autonomous. So we want people to be safe. Well, how can we make them safe? If they drive too fast, well, we want to inform the police if they drive too fast, without putting, without them knowing about it. It means covertly we want to detect whether they're going fast, how many people are in the vehicle. That's another thing we want to know. Why? Because in high occupancy vehicles, there are limits, right? So if you drive alone, then that is a violation. We want to inform that. Because we don't want it to misuse vehicles. So these are the things we are getting involved with in transportation. In healthcare, we have, of course, a lot of back-end processing that we do. We also want to do things like smart hospitals. I think there were a couple of cars this morning, hospital. I wasn't here this morning, so if it's a repeat, forgive me. We are looking at autonomous solutions for hospital environment. You know, like hospital beds, having all kinds of idle sensors in the bed and informing to the doctors or wherever within the hospital environment, or have remote sensors. And in fact, this talk is going to be with non-contact remote sensors. So how can we really measure things like physiological state of patients, and also of healthy individuals? Why do we care about physiological state of healthy individuals? It's because they may be lying, when they're debating, right? So you want to know whether people are lying, right? So when people lie, it turns out that their physiological state changes. Well, what changes? Their heart rate changes, right, when they lie. It turns out that their respiration rate changes, they're all covered. And also the temperature on the face, especially in the periorbital region. So there's a slight change in temperature when they lie. Turns out that the polygraphs are pretty good, about 80% accurate. But the problem with polygraphs is you have all these wires going by, and somebody who's smart can say, no, I know how to control these polygraphs. So they will be very cautious, right? Not, I'll control this physiological state, really the right detection. Whereas if you can do this non-contact and without them knowing about it, right? Like I'm giving a talk here, if I'm lying, if you come to know about it, isn't it good? Right? So, or maybe you have some of these videos that you want to really go back and inspect whether they were really lying. Put that into a system, and if there's a smart system, it will say, oh no, this is the area you want to concentrate. Okay? So those are the things we want to know, and in fact, things are happening already. Look at this. This is in Bradford University. By the way, I have to take out the picture because our legal is not allowing me. So the image that contains a person sitting in front of the camera is an RGB camera and a thermal camera. So what is RGB camera doing? Doing the respiration rate, and also it's extracting the heart rate. Okay? And the thermal camera is looking at the face and detecting the change in temperature. So this lie detection system is completely non-contact, and the professor says it can be about 90% accurate. Okay, polygraph systems are only 85%. So here's the challenge. I think some of you here can change the projects now. This will be pretty good if we make it 100% accurate, right? So again, it doesn't mean that we are already getting into the business. I'm just giving you, food for thought. These things are possible. They're not out of reach. So it is possible to detect lie in people if you can detect the physiological state, transient physiological. Then here is another news that came from MIT. In fact, last year I saw this as a paper, also a couple of papers, and also there was a video I couldn't show here. You can go to the website and look at it. If you go in front of the mirror every day morning, then the mirror will show you a heart rate. How do you do that? You put a camera there, and of course, signal processing to get the information. So all of this is important from a cyber-physical system perspective, because we're all in the connected world now. If we are sitting here, and if there's a camera which can intelligently look at people's physiological state, again, you might question, oh, why do we really want to keep that information? in some places it is important for security, right? So there are a lot of people over there, and some people might be dangerous. You want to know that and filter that out, right? So, and also things like minute cleaning, where you want to go and get the heart rate or your other vitals immediately. Right? So sleep studies, right, where people are lying and you want to know how their brain is functioning during that time. You don't want any contacts while taking this information, right? You want to make it non-contact. So there's a lot of applications. I'm going to talk about some of them. Here is another thing from academics. From Georgia Tech, they came up with a tricorder-like medical scanner. This is this uses 4 filters, narrow band 4 filters, between 4,000 nanometers to 1,000 nanometers. I'm going to give you a feel for all this in a moment, because this is important. So all non-contact means using some other thing, right? So what wavelengths can you operate, and what is important for what? Like there's thermal wavelengths, right? So long wavelengths and things like that. So I'll give you a feel for that. And the Georgia Tech actually developed this with a 20 nanometer bandwidth filter. 4 of them they used to detect some of the, actually to diagnose, it's not for sugar detection, for medical diagnosis. There is some skin disease that they can detect with this. Okay, so I think if you go to the website, you'll get more details on that. But the point I was trying to make here is these devices are coming, and we can probably get benefited in the society. So here is another one. This is from Star Trek Sick Bay detects diseases. So you have a control room, which is this, and a patient area. Things are, again, some of them are contact and some of them non-contact, but the idea is if you had a non-contact camera system, it will be even better, to do some of the vitals and various things. Okay, so let's just look at the electromagnetic spectrum and get a feel for what this is all about, this non-contact remote sensing. If you're familiar with this, the physicists are, and also maybe electrical engineers, you have the spectrum from gamma ray all the way to, let's say, radio frequency. But what I am talking about here for light is between visible and infrared. Okay, so of course you can also do sensing in the microwave. I know some people are working on non-contact, sugar detection with microwaves, but infrared is another region. Now look at this visible. If you have the light that you're seeing here, which is with our naked eye, you can see that between 400 to 700 nanometers wavelength. Okay, so this is visible, and you have this 400 nanometer light, which is shorter wavelength, and if you penetrate the skin with 400 nanometer light, it doesn't go inside. It is just on the surface. Okay? All the reflected energy is right from the surface. Whereas if you go to around 700 nanometers, the reflected energy will be from internal the skin, which is like epidermis or even hypodermis layer. Okay, so dermis and hypodermis layer. I'll give you a feel for that one in a moment. If you go further to the longer wavelengths, like above 700 nanometers, say for example from 700 you go up to 1,000 nanometers. Okay, so that is actually the near infrared. By the way, you can see about 750 nanometers or 800 nanometers, you can actually see that light. It is not that bright. Bright red is about 700 nanometers. Okay, so about 800 nanometers you can still see a little bit. But if you go to around 900 nanometers, you can't see that light at all. If you have this area illuminated with 900 nanometers, nobody can see it. Okay, so it's basically completely covered. But the problem is, all of the energy that you can detect in this wavelength can be done only with CCD detectors and CMOS detectors. CCD detectors are very cheap. CMOS is also cheap. But if you want to detect higher wavelengths, above 1,000 nanometers, say for example into the shortwave region up to 1,700 nanometers, that's where, by the way, you can do sugar detection. If you're trying to find a way to do non-contact sugar, this is the wavelength to worry about, 900 to 1,700 nanometers. Okay. So, the sensors, particularly the cameras, are very expensive. between this 900 to 1700 nanometers. Okay? Now, going beyond this, like 2500 nanometers or even 3000 nanometers, well, there is a problem. You can't use all of those wavelengths. Look at this diagram. This is a spectrum of the reflected energy for very wide infrared wavelengths, up to 14,000 nanometers. Okay, this is about 700 here. 700 to 14,000 is covering about less than half of the infrared. So we have quite a lot of infrared here after 14,000. Okay. Now, if you look at this carefully, from 5,000 to around 8,000, you cannot see anything because when you penetrate with that IR, the water molecules absorb everything. So you cannot get anything out of the reflected energy. You can't detect it. It's completely opaque. This 5,000 to 8,000 nanometers. Now, if you come below that, up to 3,000. By the way, all of this is emitted energy, not reflected, because bodies can emit it. A body is black body radiation, right? So, here also it is emitted energy. Okay? So you have a black spot again in the mid-wave infrared between 4.2 to about 4.7 nanometers, micrometers, sorry. It's hard to remember all of these. Then here is another region. It's pretty opaque because of the water molecules again. Okay? So you can't really detect every region perfectly. Okay? So this is to remember. And also the cost of the sensors. Some of them are pretty cheap and some of them are expensive. As I said, 900 to 1700 is very expensive, about $50,000 per camera. 1,000 to 2,500 you can get for about $36,000. And when you go to 3,000 to 5,000, by the way, if you want to detect carbon dioxide coming from all that, this is the wavelength to worry about. It's between 3,000 to 5,000. Okay? So the cost of the cameras is not that expensive compared to here. And if you want to detect the temperature in the human body, you could use this wavelength as well as long wavelength. Okay? So these cameras are pretty cheap, $2,500 to $11,000. But they're not as cheap as the CCD cameras. CCD cameras are $120 in a video camera you can get. So, in fact, next thing you're going to see is how can you detect, pulse or heart rate with CCD cameras because they're so cheap, right? You can also detect heart respiration rate with that. Okay? Well, before we can do this, let's look at the anatomy of the skin. By the way, I am a control engineer. I had to learn a little bit about human anatomy, so I started taking these courses. So if you want to do anything in biomedical, I would advise you to take those courses, anatomy and physiology. Otherwise, it will be very hard to understand this medical language. So here is one example. So this layer, this is the top layer of the skin. It's called epithelial layer, okay? And most of this layer is made out of this stratified squamous epithelium. Why is it epithelium? Well, this doesn't have any blood vessels. By the way, it's several microns thick. It depends where you are in the body. Okay? On the face, the whole skin, the cutaneous layer, which contains this epithelial and dermis layer, basically this is called epidermis, which is the epithelial layer, and then the dermis layer, and then the hypodermis. So the skin is actually this dermis and the epidermis. Okay? So this is about half a millimeter on the face, whereas on the hand, this is the callus region. It's about 1.5 millimeter. Okay? So where are the blood vessels? Well, the blood vessels are actually in the hypodermis. This is in the subcutaneous layer. Okay? So these are pretty large blood vessels compared to the capillaries that go into the dermis and supply the blood to this layer. Okay? And there are a lot of other things you can see. And when the light falls on the skin, well, there is a lot of opportunity for the light to scatter, right? Scatter from the surface itself, like blue light I said. It scatters right from the surface. And then red light or near infrared can go deeper and can go all the way down up to the hypodermis layer and reflect back. Okay? Now, if there is blood flowing through this, which is the case, right? If you're on the line, we want to test this on live people. So, for live people, there is pulsatile blood. I mean, as blood flows through these vessels, there is, you can see basically the shape bulging. Okay? And when the light goes through this, it passes and then comes out, you start seeing the change in path length. And there's some absorption that goes on because it's more blood and less blood, right? So, and there are sensors called PPG sensors. These are photoplethysmographic sensors, and those sensors actually detect the volumetric change. And with this camera-based system, that's exactly what we are doing. We are detecting the volumetric change in blood, provided it's a video camera, not static camera. Okay? So, well, there are these cheaper sensors available. These are contact-based. For example, this is in pulse oximeter. The pulse oximeter uses two LEDs, one in the red and one in the near infrared, around 900 nanometers. And using two LEDs, you can detect the change in oxygen level in the blood, and also you can get the heart rate, because this is actually transmissive. The light actually goes through the finger, and it's a finger oximeter. So it goes through the finger, and it turns out that the finger is a terminal point for all these arteries and veins. Because there are a lot of arteries here. So there's on your hand, there's a radial artery, there is a ulnar artery, and there's interosseous artery here, and then it branches out. On the back of your hand, there are veins. So on the finger, there is a joint. And so because these arteries, they turn into capillaries and then come out as the veins. And so when this sensor operates, it actually shines light through the finger. And as blood moves it through the finger, you can feel it actually, if you are careful and observing this very carefully. The change in light, you can see it in the transmitted light. And if you put a probe, you'll start seeing the signal. By the way, we did this experiment even by using a camera. So what we did is we put a light, LED underneath, and then had a camera about 3 feet away. So we were able to see the heart rate with the signal. So the transmission does work, even in a finger like this at a distance of 3 feet. So these are very cheap, but the problem with these contact sensors is for neonates or babies or infants, if you put these contact sensors on their fingers can break because they're so delicate. And by the way, we are working with a hospital in India, Manipal University. We put a couple of cameras in the intensive care unit where they bring all these newly born babies. They're just 1 month or 2 months old. They're not normal, so that's why they're in the intensive care unit. And the doctors are saying, if you can come up with a non-contact measurement system, it's fantastic for a neonatal. Because neonatal really needs it, if you can make it work effectively. But it is not easy to make it work effectively for neonatals. You'll see it in a moment. Why? Well, let's look at the signal for normal adults, like you and me. He's Orlando, he's in our lab. I think Takashi has met him. Yeah. So Takashi was our intern and he did some work in the heart rate. By the way, I didn't put your results here because they haven't finished covering the intellectual property. So otherwise that would have been nice as well. Orlando is sitting here. He's around 8 feet away, by the way. I magnify it. And this is a $150 camera, video camera, RGB camera. We focused on his face, and if you take each video frame and convert that into one value, how do you do that? Well, let's say in this particular case, we're not doing any face tracking. We're taking the whole region, okay, average it, and average every frame, okay, so get the global average, subtract the global average with the average of individual frame, okay? So you get a signal. Right? And then divide by the standard deviation, you get a normalized signal with unit variance. And that becomes our time series for every channel. So red channel, green channel, and blue channel. Okay? So these channels, by the way, it's not just the red channel which carries the signal, the smoke signal. Even the green channel carries it. And a little bit in the blue also. Because the blue, if you look at the detector response of blue has a little bit of light coming in the red region, especially around 6 blue is not completely opaque to the red. So you have in every channel a little bit of a signal, but red has probably not more than the blue, whereas green has a little bit more because it's right in the middle. So all these three channels contain the information we're looking for. Now, how do you separate that? Because it's a time series signal. Now, if you do just the FFT of that, well, it contains motion as well, right? In this case, he's sitting quietly. He's actually, he didn't even open his eyes because there was light shining in his face. But in the normal environment, people are doing their thing. They're moving around, right? So you have motion involved in this as well, this signal, time series signal. Not only the signal that's related to heart rate. So what we did is we did what is known as an independent component analysis. This is an elegant approach that people have devised in statistics. There's a good theory behind this. There's a lot of papers that have come out. The independent component analysis basically separates the sources. And it's used very widely in medical field, by the way. What it does is, so if you have these three channel signals are fed as input, you have to create a demixing matrix to separate the independent components. So the way you separate them is through iterative techniques. You have to create a performance function where the performance function tries to find the independent sources, the sources that are separate from each other. Like signal 1, when it changes, signal 2 doesn't depend on signal 1. Okay, so you have to look for those kind of signals. So that kind of separation is done, and then we do the power spectral density and things like that. So this is this power spectral density curve for against the frequency. You can see a signal which is very strong at around 59 beats per minute. Okay? Well, there is also a signal related to motion, or eye blinking and things like that. And there is another signal here which is related to the background noise in the camera. So we have to separate this as well, right? So out of these signals, which one is heart rate? We have no clue. We have to remove signals like this. So in fact, there are techniques we developed internally to remove the background noise and camera-related signals and things like that. And in fact, out of this, the signal that is at 120 beats per minute is actually camera-related signal. You can see that by taking a chunk of this video and processing it through the same algorithm. Yeah? So if you do that, this signal disappears because you don't have that. That is the heart rate signal. And this one is actually related to the camera calibration signal. So we separate this out and then retain only the heart rate signal. In this case, it turned out that the finger oximeter gave 58 beats per minute and the algorithm gave around 56. By the way, for normal human beings, the rest heart rate is still varying. It's not constant. Okay, so it's not exactly 58. The finger oximeter gives an average number. And this was taken over a period of 1 minute.
What's the x-axis?
X-axis is the frequency, the beats per minute. It is in terms of minutes. So this is actually close to 60. So you have 1 beat per second. Okay. So any other questions? Right. Well, if you understood this, then the next slide will be easy. Well, in blind source separation, or in ICA, what happens is you get, no doubt, 3 independent components. In here, we had RGB signal going in, and then we did the blind source separation. We got 3 signals out. We call them source 1, source 2, source 3. And one of them contains the heart rate. Why? Because the blind source separation, or ICA, actually assumes that these sources are actually linear mixtures, and it separates the mixtures, okay, and gives you the sources, but sources could be arbitrary, like heart rate could be in first channel, or could be in third channel, so it will be switching around. You want to be consistent, right? You don't want to be always in, you don't want to be in S1 or S4 or S3. You want to be consistent in one channel. So we had to come up with a new algorithm for that. This is the constrained source separation algorithm. In constrained source separation, again, I couldn't put all because of legal reasons. So, the Xerox legal is very strong in this. They don't allow us to show any mathematics, and nobody talks about mathematics inside because they're all anyway. So we don't want to go into that situation here. So the constrained source separation, what it does is, say you have an individual, the heart rate should be, a healthy individual is experiencing 50 to around 120 beats per minute. Okay? So you have that range, and you can create a pseudo signal, which is just a square wave, with a range of say 50 beats per minute. Okay? For 50 beats per minute, find an independent source out of these three channels. Where I find something and compare the frequency of the output to the reference, you find, oh, there's a large error there. Change the frequency again from 50 to go to 60, okay? Go to 70, do the same. At some point, you will see that the error is low. Okay, so that's what the constrained source separation is doing. And so it is constrained by the a priori knowledge, right? Because you know this individual has a heart rate of around 50 to 120. Right? Well, that is not the case in infants, by the way. Infants have a very high heart rate. It can go up to 200 beats per minute. Okay, so so we did this work, and in the constrained ICA algorithm, we got much better results compared to the ICA algorithm. In some cases, you could see there was the numbers were not very accurate. So this is around 66 here compared to 72. This is a video 8, and the constrained source separation gave very close numbers. So again, all of this depends on what kind of algorithm you use. It's not an easy thing to separate the sources. Okay, so here is another example for a non-cooperative mode. Because person doesn't know, we're really taking a video, and we did the face tracking as well as no face tracking. From 84 and constrained source separation gave around 85, 90, 92. So you can see these are all pretty good numbers. We've taken quite a lot of videos in this. Yeah, so with non-cooperative. By the way, the camera here is a webcam. So, and constrained source separation is our algorithm. We're going to publish this in a couple months. So if you're interested, you can look at our publication. We developed this algorithm in collaboration with RNP. And the ICA is a prior art. People from MIT published that, and we tried that algorithm straight away, and we didn't find great improvement. So, okay, so next. We also tried for 2 individuals do this simultaneously. In this case, video was taken for about a minute, and it's about 1 foot away. Okay. So, by the way, we have enormous data, even with 8 feet to 12 feet length. So it is possible to do this heart rate estimation. And for multiple subjects or single subject, this shows the results for about 9 feet distance. So you can see as the individual is farther away, and if you don't change the zoom, the pixel width you're going to get is as big as the blood vessel. You may miss the blood vessel, right? So you'll have to use the zoom as you go along. So that means in this room, theoretically, we can get the physiological information, particularly the cardiac information for everybody.
Are the results good enough to predict arrhythmias?
Yes. Yeah, there is a. I don't have the results here. We're looking into that. Sinus arrhythmia is another thing we want to predict because just to, so that everybody is aware of this. What happens is not everybody's heart rate signal is beating at the same rate. So when heart pumps the blood, like there is systolic and diastolic pressure, right? So you have the waves, changing their frequency. And so you have interwave beats, right? So that interwave beat is an important cardiac information, and that is related to the I think peripheral nervous system interacting with the autonomous nervous system. So the sinus arrhythmia is an important diagnostics, especially for infants, and that's something we can get out of this. It's a different signal processing, same signal. You do a different kind of signal processing. You have to get low frequency and high frequency ratio to do that. Yeah, that is possible. And not only that, there are other things like cardiomyocytes. You may have heard of this. This is where we are growing older. As you grow older, over 40, not many of you are over 40. I am over 40, and there is a cardiac risk of heart attack. And by looking at this ratio. And imagine the value out of this. You have a camera continuously monitoring, and you are not aware of it, but it gives you a number. It says, oh, today you have a risk of this many percent, right, of heart attack. Well, I would like to know that, right? Well, my heart may not be pumping blood very well today, but I don't know what is going on. But if this intelligent system can give me that information, it's very valuable. So, other question?
Just in the last slide, and just the definition, when you had two people, what was the meaning of ground truth? Which person?
Oh, we had ground truth for each one of them. We had two instruments.
Okay.
Yeah, in their hands. The finger blood volume pulse meter.
Well, so I mean, it's looking at that one video, and did you just pick it had one number corresponding to that one video? Did you just pick one of those people, whichever one it matched? I mean, I guess.
Oh yes. In fact, person 167. This is person one. Sorry, I didn't explain this very well. That's why I wanted this to be interactive. So ask me questions. So, I'm pretty good when you ask questions. I can bring out more information, as I said. 67 was person one, and that came from the finger oximeter she was holding.
I just didn't notice the extra column in that. I see.
Yeah. So person two was for the second person. Yeah. They both were students, by the way. So. Yeah. And in theory, we can do this simultaneously for more people. We just need wider field of view and resolution, high resolution cameras, or you can move the camera. And other thing is, this was done for a single shot, 1 minute video. You could do continuous monitoring. So there are many things that can come out of this.
Well, if you did that as one shot, you weren't panning, and you've got a bunch of these signals out, 10 different pulses. How would
it?
Yeah.
Well, look at it this way. The light that is falling, again, we didn't have our own focusing on this. It's normal room light. Okay? So it's fluorescent light. Fluorescent lights don't have a lot of IR energy. It's all in the visible. So both of them received light, slightly different amount, but the reflected light has scattered light as well, right? Light coming from the person one as well as light coming from person two. So it turns out that the signal, that source signal, when we did the blind source separation or the constrained source separation, the source signal that came out of this segment of the video was dominantly because of this person.
So you're able to actually.
Yeah. We had to segment it. Yeah. There's a lot of image processing that goes on behind this. Yeah. These are the things I could not put it out. So there is also. This you have to do many things like whitening, where whitening makes the decorrelation of these channels prior to doing ICA. So if you don't do whitening, you don't get the signal accurately. So there are a lot of things that go inside. And what kind of filter you use, like long filters, some of you may be familiar, long period. You may be familiar with that. So you have to use those. I didn't use long period in this. So there's a lot of signal processing that goes in behind this. But the key part is this normal video contains that information, right? That is very, very interesting. I mean, whenever I present this to people in Xerox or outside, they think that this is some fiction. And again, this is only for heart rate, but I want to do this for all kinds of vitals. Vitals contains not just heart rate, you have blood pressure. Well, you can think now, how do you get blood pressure out of this? Well, it turns out that this when you do the ICA, there is a signal that comes out of it, which contains the volumetric signature of the blood that it has sensed, because it's not just at one point; it is the integrated region, right? So now, what I'm thinking is maybe I can do this in two regions, like proximal to the heart and distal to the heart, and get pulse transition time. Right? Once I get pulse transition time, I can relate that to blood pressure. Well, it's cool, right? Now, look at the light detection we can do. We can do blood pressure, we can do, this is all science fiction at the moment, right? If we can do blood pressure, if we can do heart rate, respiration rate, okay, and of course temperature using the thermal sensing, it becomes a lot accurate. So that's our goal. How do we do this is, again, quite involved. So if some of you want to work on these projects, let me know. So Okay, any other question?
Are there any requirement on what part quality you take? Because you always show face.
Well, that's where I said understanding the anatomy helps a little bit. The integumentary system is the skin mainly. Like face, if you want to do this covertly, without people knowing about it, then best thing is to concentrate on the face. And it turns out that face has a lot of blood vessels. The carotid arteries here, and also jugular veins, they go into the face, and ophthalmic veins as well. Most of the signal we capture with this is through the veins, not through the arteries. Because the arteries are a little bit deeper. Yeah. There was some work done by Professor Pavlidis from Houston University. He did the work by looking at the superficial veins right here in this region. So again, for infants, I'm thinking, oh, why only face? Because infants in the ICU, their body is exposed except this region, abdominal region, so pelvic region. So this region is exposed. So we can get a lot of information here because if you look at the heart anatomy, there is aorta going, near these vertebrae and then coming back through the through this diaphragm and into the abdomen. So if you hold your hand here and here, you see the differential pulse. Now you can try it out tonight. Okay. So it's pretty magic, and the information is there. You just have to work on it, right? So. Okay, any other questions? Well, talking about infants, this is actually a video image we took in Manipal University. How many of you are familiar with Manipal University? Okay. And we have cameras in the ICU unit, and it's a couple of years project. This is actually the time series of the whole region of this baby. Okay, not just the face. Okay, so it's like even here you have arteries here, you have aorta here, and the blood vessels, So, and there are a lot of regions we captured, and the signal looks actually crummy. What can you make out of this signal, right? So, if you do the source separation, it gives you very good information. Look at this. This is pretty significant. I mean, this is the heart rate, basically, and the motion. Baby was not moving that much. Even if it is moving, it's much slower frequency compared to the heart rate. So in this particular case, the baby's heart rate was not changing a lot. It turns out that for neonates or infants, the heart rate changes very rapidly. This is where the challenge is. In fact, if you want to do some research to separate the signals, if you can do this for cases where the heart rate changes very rapidly, when I say very rapidly, in 10 seconds, their heart rate can change from 80 beats per minute, which is my heart rate, by the way, to 180. Okay, more than double, actually, in 10 seconds. So it is that fast. So how do you detect when the heart is pumping blood, so rapidly and so with so much variation? So that is very hard. We are facing that problem now because the heart rate is changing so rapidly, and I don't think we can pass the FDA without coming up with a good solution for this.
Have you considered using different cameras rather than just focusing on CCDs to solve this problem?
Yes, we have done quite a lot. In fact, we have filed a couple of patents in that space using multispectral NIR as well as shortwave infrared. Shortwave infrared wouldn't work that well except for lower wavelengths like 900 to 1,000 nanometers because the blood which is oxygenated or deoxygenated blood has a very low signal content after about 900 nanometers. And so up to around 900 nanometers, you have very good signature from the blood. So that's why we didn't do much work with the shortwave infrared for this particular case. It's all in the with the RGB as well as the near infrared. Okay. Any other question? No.
What sampling rate are you using in order to get 120 beats per minute?
That's a very good question, yeah. In fact, sampling rate is important here. In this case, baby's heart rate was very high, well, about 130 here. In this baby, it was 160 beats per minute. We still use 30 frames per second camera.
How do you prevent like aliasing or like visual signal processing?
There's a lot of that goes inside. Yeah. So there are a lot of cool ideas, new ideas as well. If heart rate goes to 200 or 220 and still not change the frame rate. So we are, those are things we are working internally. So we can talk offline if you want to know more. And by the way, a couple of videos I took earlier, they were all at 15 frames per second, much lower speed. Okay? Yes, frame rate is important. Okay, any other question? Okay, so benefits, you already heard some of the benefits for this kind of technology. And again, the benefits could be even more if you add other vitals, like as I said, like respiration rate or sugar detection. I don't know whether anybody is doing sugar detection here. I would be very interested to probably done. Okay. I want to do non-invasive sugar detection, okay, with cameras, because cameras will help us to identify the vein pattern or the arteries. Okay. And then once you identify those are the tracks I can use to detect the sugar. And if we detect the sugar, with our combined efforts, world will be a better place, right? There's so many diabetic patients. They want the sugar to be measured continuously. Yeah, and there is a lot of demand for that technology, and nobody has it. Yeah. So with heart rate itself, of course, the neonatal and infant ICU will get most benefits, and we can extend that to adult ICU. But if I pass this test in the hospital, I think this will become a commonplace in adult ICU, because adult ICU is a piece of cake. And even the rooms like this will be a piece of cake. Because infant heart rate is very difficult. It changes so rapidly. Okay, so that's the biggest problem for us. Also, signal strength is not bad in the infants because the epithelium layer is small, and the hypodermis is very close to the top layer. So hypodermis and dermis layers. So, the doctors were telling me that if they see this working for respiration rate, heart rate, and also oxygen saturation. By the way, we can also detect oxygen saturation with this, just like the pulse oximeter. This pulse oximeter is doing what? It's looking at the ratio of the signals for the red and the infrared. Okay? So it's the change in the oxygen level in the blood, and that signal is present in this the pulse we are getting out of this technology, but we haven't separated the oxygen yet. Okay? So that's another thing. If we do, then we would have covered quite a lot of vitals. So and if we have this technology available, then all this emergency room, access becomes very easy, right? So you just walk through the door. So you have the camera taking all of the information and readily available in the emergency room. So and also when people are sitting in the emergency room, you have the vitals taken. Nurse doesn't have to go and do that on an individual basis. So a sleep study I already mentioned, lie detection, monitoring at home during interviews, talks, debates, right? So this will be very, very good. You can create some rumors on politicians, right? So which I think will be good.
Have you run this during televised debates?
I don't want to say any of that yet. I don't want to say anything. So, but I'm just saying the value we can generate. Of course, not many people will go to public office without having some sense of them. So, anyway, sports application is another one. Right, training athletes, swimmers, and drivers' physiological state. So this will be very helpful. Of course, not helpful for large autonomous systems because there are no drivers there. So, but today's drivers, we would like to know that when they go to the junction, is their heartbeat increasing too much? Then they're likely to get into trouble. And the cardiomyocytes. So there are more applications, but I just listed a few. Okay, so I'm going to change gear and go to another topic. Are we done? 4:30? Yeah. Well, then I'm going to skip this very quickly. Okay. So let me just show you some results of occupancy detection. This morning, I think this afternoon, we had a challenging problem in a building. I don't think they're here. Detecting occupancy is a major problem, right? It is a problem, but if you use RGB cameras, we would be able to get, I think, pretty good accuracy, inside the room. But outside, if you want to detect the occupancies, then RGB cameras are not good because the detection is based on shape. Why it is not good? It's because people use dummies. They fool us, right? So if you have a dummy sitting next to you and you have an RGB camera saying, oh, there are two people, actually there are not two people, there's only one person. Another one is a dummy. So you want to be able to separate the dummies. Okay, so to separate the dummies, we have come up with a different technology called skin detection technology. So basically what we do is use multispectral approach to operating in the infrared, especially in this region, in the shortwave infrared, because in the shortwave infrared, the skin has a spectral content very similar to the water absorption spectra. This is the water absorption spectra, okay? And this is the skin spectra. And you can see somebody who is dark has this spectra, and somebody who is white has similar spectra. So it's dark and white people look alike in this wavelength. So in this infrared wavelength. So what we do is we use multiple channels, image them simultaneously, and then do the image processing to separate. Okay? And here is an actual example of a human sitting in the vehicle. We shine light. This is the infrared light, and do the multispectral detection. We can say, oh, there is one human. This is basically detecting only skin, this region. Okay? You can see a blob here, and we count this blob. Say, okay, there's one person. In this one, we have two people. Okay? If you have a dummy here, then you don't see this. Okay, so we can separate the dummies. Okay, so basically non-contact remote sensing has a lot of value, and it is part of cyber-physical systems because they're all connected to the internet. Okay? So I think we have a great opportunity to make a good business as well as create a lot of papers, you know, and PhDs. So okay, thank you for your attention.
Take 2 questions. The previous slide, was that some kind of a texture classification?
This one?
Yeah.
No, we did, how many channels in this? This was imaged with 3 channels, 3 spectral channels. So there's one wavelength here, one wavelength in here, and another one right here. Okay, so you get 3 images, and then apply our model-based skin detection technique. If you want to know about it, I think the patents will be publicly available, patent applications, very soon. So we'll file quite a lot of patents in this space. And you can take a look at it. So everything, all the algorithms are described in that. So okay, and basically our approach is to detect these blobs, and we can separate these blobs because of this multispectral signature.
Does it differentiate between real human face and a photograph of a human face?
Correct, because photograph doesn't have hemoglobin. It doesn't have water content inside. Well, some people ask, okay, what if I use a dummy with a wet cloth on the face? You know, it turned out that we could separate that out. So they can't, and people can fool us, right? So we about 0.5 millimeter you see the hypodermis in the face. Like in the eye, there is, you directly get the dermis layer. There is no epithelial layer at all, the top one. The epithelial is the layer where every 15 to 20 days your skin, you get new skin. Okay, so they're all keratin cells, so they're dead cells basically. Okay, so light still goes through that. Yeah, and into the dermis and the hypodermis, you know. So that's a good part. By the way, the infrared, longer infrared wavelengths, they go even deeper, about an inch deeper. So you could get a lot of things like muscular, shapes, whether it's we haven't done those experiments. So,
Just
but
out of curiosity, what rays do they use in MRI?
MRI is very different. They have to put in electrolyte, I think, electrolyte or catalyte. Some compound.
Classify that as contact rays detection, where the sensors can make contact.
The MRI imaging is based on some compound that they have put in. I forgot the name of that compound. They have to give that to the individual. Then it flows through the blood, and okay, and you image that because when you do the MRI, it is based on resonance imaging, right? So magnetic resonance imaging. So you have to have dipoles created inside. Whereas this one is not. This one is you're not taking any drugs or anything. So that's why the hospital staff was very interested in getting this to work because it's easy to pass the committee reviews. If you have good data, then they say it's okay because we're not giving any drugs. If it matches with the FDA approved instrument, then we're done.
Okay. I was just going to ask, would this be useful in detecting skin cancer, looking for sort of differential patterns?
I think it will be, may not be exactly what I did, but if you can get the spatial information, it may not be able to detect deeper skin lesions, but if they're on the subcutaneous layer, then you may be able to do that. I've heard some presentations related to that from University of Rochester. They have done some work to detect the skin cancer. It may be like malignant, not completely fully cancerous. So, yeah, those are the other prospects. In fact, the IR energy, it is not, if you don't put a lot of light, then it doesn't burn anything. So it goes deeper as well, so you can get a lot of information out of that. One of the problems is this is the optics challenge here, because the light that comes out has specular content, scattered content, and all of that. If you know how to remove specular, for example, using polarization, the right kind of analyzer and polarizers in your imaging path, so and illumination path, so then you may be able to get better structure, and 3D imaging, there is this structured lighting that is coming in. So in structured lighting, you illuminate with dots, and you can get a 3D because the dots are penetrating differently based on the depth, right? So that will also play a big role in the future. So we're trying to collaborate with the University of Arizona on some of that. So, yeah. Any other questions?